Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about thermodynamic equilibrium. So first of all we should know what is thermodynamic equilibrium. We will discuss some other equilibrium process before the thermodynamic equilibrium. One is mechanical equilibrium. The other is thermal equilibrium. One is chemical equilibrium, and the fourth one is thermodynamic equilibrium. So we will discuss these four types of equilibrium. Now, first of all, we will discuss the mechanical equilibrium. So we know that if the sum of force acting on a body become equal to 0, then we will say that the body is in mechanical equilibrium. For example, this is a table and body is placed on it. There will be two forces acting on the body. One will be the force exerted by table on the block or body. So it is denoted by F1, and the other force, which is the gravity of the block, it is denoted by F2. So this is F2, this is F1. Now the F2, suppose the direction of F2 is downward and the direction of resulting force is, which is F1, is in upward direction. So F1 is equal to minus F2 in this case, and F1 and F2 are same in magnitude. So F1 plus F2 will be equal to 0, or the sum of forces acting on this body will be equal to 0. Similarly, consider another body. So this is the right force. Suppose it is F1, this is F2, and two forces, this is F3 and this is 4. So if F1 force is equal to F2 force, F2 force is equal to F3, and it is equal to F4 force, then this body will be called in mechanical equilibrium. So similarly, for rigid body, the second condition can also be applied, that the sum of torque acting on a body is equal to 0. So clockwise torque acting on a body will be equal to the anti-clockwise torque. So if the clockwise torque is equal to the counterclockwise or anti-clockwise torque, if clockwise torque acting on a body is equal to the anti-clockwise torque on a body, then we will say that the body is in mechanical equilibrium. So suppose this is one torque acting on a body, this is the other torque acting on a body. This is the clockwise torque, and this is the anti-clockwise torque. So if these two torques are in same magnitude, then we will say that the body is in mechanical equilibrium. So suppose it's a circular string of a car, suppose. So we will say that the body is in mechanical equilibrium. The second type of equilibrium is thermal equilibrium. So let us consider two body. This is body number 1 and this is body number 2. Okay, this is body number 1, and this is body number 2. So suppose the body 1 is at high temperature. See, body 1 is at high temperature and the body 2 is at low temperature. See, body number 1 and the body 2 is at low temperature. This is body number 2. Now these two bodies are connected with each other. This is the area. Now the temperature of body 1 is high and temperature of body 2 is, suppose temperature of body 1 is T1, temperature of body 2 is T2, and the two bodies are separated from its surrounding. Two bodies are separated from the surrounding. The temperature of body 1 is high, then temperature of body 2. So heat will transfer from the high temperature body to the low temperature body. So after a certain time, the temperature is the heat transferring from the high temperature body to the low temperature body. The temperature of this body will decreases with the passage of time, and the temperature of this body will increases with the passage of time. So similarly, the thermal resistance of this body will decrease with the passage of time, and the thermal resistance of this body will increases with the passage of time. And the heat transfer which transfer from this body to this body will be denoted by K, dt and dx. This is the distance through which heat transfer. This is temperature difference, which is nothing but T1 minus T2, and this is the thermal conductivity, and this is the area for the heat transfer, and it is the heat rate. It is nothing but the Fourier law of heat conduction. Now this area is denoted by this black surface. This is the area for heat transfer. Area for the heat transfer, this black one. So this is now when the temperature gradient become constant, when there is no temperature gradient, then the heat transfer will be equal to 0. So if temperature become constant, then no heat will transfer. So a time, so as the two bodies are in contact with each other, the temperature of this body will decreases and the temperature of this body will increases with the passage of time. After a certain time, the temperature of this body will be equal to the temperature of this body, and the gradient for the heat transfer will become equal to 0. So when a time reached, and so a time when the temperature of this body becomes equal to the temperature of this body, we will say that the two bodies are in thermal equilibrium with each other. So this is the thermal equilibrium. So simply this was body 1, this was body 2. These were isolated from the surrounding. The temperature of body 1 was T1, this was T2. The heat was transferring from this body to this body. After a certain time, the heat was transferred from this body to this body, and when the temperature of this body is equal to the temperature of this whole body, then we say that these two bodies are in thermal equilibrium with each other. So this is the thermal equilibrium. Now another type of equilibrium is called the chemical equilibrium. Chemical equilibrium. Now what is chemical equilibrium? A body is said to be in chemical equilibrium if the escaping tendency of one phase is equal to the escaping tendency of another phase. So it is the escaping tendency, it is nothing but the chemical potential or component. So suppose this is a beaker, it is filled with some water to this position. This is the water. Now when you give some heat to the water, then the temperature of the water will increase. So the molecular motion of the water molecule in the liquid will increase. So after a certain time, the water will escaping from the liquid toward the upper space. So this is the upper space, upper empty space. So when we give some heat to this system, then the water molecule will transfer the temperature of the water molecule in the liquid will increase. So the motion of water molecule in the liquid will increase. So after a certain time, the water will come to the surface and it will escape from the liquid water to the open space, the upper empty space. So this is the water molecule in the open upper space. So when we give further heat to the water, more and more water molecule will transfer from liquid to the vapor. More and more water molecule will transfer from liquid to vapor. So this is called the rate of vaporization. So when we give heat to the liquid water, the rate of vaporization will increases with the passage of time. Now, after a certain time, some of the water vapor molecule will convert it from vapor to the liquid water again. This is called the rate of condensation. So when we give heat to this liquid water, the water molecule from the liquid state will convert it to the vapor state, which is called the rate of vaporization. After a certain time, some of the water vapor molecule will condense to the liquid water again, which is called the rate of condensation. Now when we continuously give heat to this system, a time will reach when the rate of vaporization will be equal to the rate of condensation. The rate of vaporization will be equal to the rate of condensation. Then at that case, this system will be called to be in chemical equilibrium. So suppose three molecule is converted from liquid water to vapor. Then at the same time, the three molecule of water vapor will condense to the liquid again. Then at this time, we will say that this system is in the chemical equilibrium or dynamic equilibrium. So chemical equilibrium is a dynamic equilibrium. So after a certain time, first of all, this was liquid water, when we give heat to the liquid water, the water molecule from the liquid will convert it into the vapor, which we call the rate of vaporization. After a certain time, some of the liquid molecule will convert again to the liquid water, which we call the rate of condensation. Now, after sufficient time, the rate of vaporization will become equal to the rate of condensation. Then at that time, we will say that this system is in chemical equilibrium or dynamic equilibrium. So dynamic equilibrium is nothing but it is chemical equilibrium. And at this time, the escaping tendency of liquid water molecule from liquid to vapor will be equal to the escaping tendency of water vapor to liquid. So after a certain time, the escaping tendency of liquid water molecule to gas will be equal to the escaping tendency of water vapor to liquid. So the escaping tendency is nothing but it is the chemical potential. So after a certain time, the chemical potential of this liquid phase will be equal to the chemical potential of this upper phase, vapor phase. So the chemical potential of liquid phase is denoted by Ui, and the chemical potential of this phase is denoted by UV. So after at equilibrium, the chemical potential of the liquid phase will be equal to the chemical potential of the vapor phase. So when the both chemical potential become equal, then we will say that this system is in chemical equilibrium. Now this chemical potential, that is nothing but Gibbs free energy per mole is equal to the chemical potential. So the Gibbs free energy for phase 1 will be equal to U1, and the Gibbs free energy for phase 2, suppose it is U2. So at equilibrium, these two will be equal. Then we will call that this system is in chemical or dynamic equilibrium. So for dynamic equilibrium, you can see the video in the description. Now, when the above three equilibrium combine, which we discuss in this lecture, one is the mechanical equilibrium, one is the thermal equilibrium, and the third one is the chemical equilibrium. When the above three equilibrium combine together, then we will get the thermodynamic equilibrium. So thermodynamic equilibrium is nothing but it is the sum of mechanical, thermal and chemical equilibrium. So suppose this was a system, this was liquid water, this was the upper space, the rate of evaporation will become equal to the rate of condensation, and there was no mechanical force acting on this system. So this was mechanical equilibrium satisfied. If we measure the temperature during the thermodynamic equilibrium, then the temperature of this system will be, suppose it is 20 degrees centigrade, so the temperature or thermal equilibrium is also satisfied for this system. Similarly, the rate of evaporation becomes equal to the rate of condensation, then the chemical equilibrium condition is also satisfied for this system. So we said that this system is in thermodynamic equilibrium. So this was all about the thermodynamic equilibrium. At thermodynamic equilibrium, remember that the driving force becomes zero. Driving force is equal to zero during the thermodynamic equilibrium. The driving force for thermodynamic equilibrium is the chemical potential, similarly the temperature gradient, and the mechanical forces. So when the forces, sum of forces becomes zero, similarly when the temperature gradient becomes zero, similarly when the change in chemical potential is equal to zero, then we will say that this system is in, when these three conditions satisfied by this system, then we will say that this system is in thermodynamic equilibrium. So thank you very much for your attention. Thank you very much.